Hello. At this point in organic chemistry, you have probably learned about 20 reactions and maybe have made several compounds in the lab. And while you know several purification techniques, there are instrumentation that helps chemists verify a product's chemical structure, whether it be a product of a reaction in lab or an unknown molecule isolated from nature. And the first type of structural identification technique I want to look at is infrared or IR spectroscopy, and it can tell us the presence of specific functional groups in a molecule. It is based on the molecule's absorption of light waves in the IR region. Now, other spectroscopies exist, such as UV spectroscopy and nuclear magnetic resonance spectroscopy, that you'll probably learn later. Those are based on the absorption of light at these other different frequencies. But I want to focus on IR, and the first thing I want to do is to define a spectroscopy. This is in Unit 13, where we talk about several spectroscopies, spectroscopies, plus a spectrometry technique called mass spec. But let's focus on IR, and let me give you a fairly long definition for molecular spectroscopy. It's measuring frequencies of radiation absorbed, typically, but sometimes emitted, and then correlating these patterns or maybe we could even call them peaks or signals, with structure. Let me see if that makes sense. Measuring frequencies of radiation absorbed or emitted and correlating these energy absorption signals with, I like that. So the first thing is, let's think of a bond as springs, and the first bullet point, we're going to talk about a molecule's vibration. Types of vibration. And the key to this is to think of bonds as springs. All right. There are two types of vibrations. There's one called stretches. And let me draw you a little cartoon. Let's take this atom connected with a bond, but we'll think of a bond as a spring to this red atom. And let me give us another red atom over here. Okay, you know that molecules are dynamic, they're vibrating. In this case, I'm going to show you a stretch, and if the red atom goes outward that way, and this one goes outward that way, that's called symmetrical stretching. Now, if they go in this direction, let's say we still keep this red atom going out this way, but this red atom now comes in, that's called asymmetrical. You don't typically need to identify these types of stretches via cartoon. I'm just showing you some examples. Because you can imagine that these stretches have now a frequency, a pattern of going in and out, expanding, contracting, and it's always happening. It's always vibrating. The other type of vibration is called bends. And let me draw it this way now. So how do we get a bend? Well, we could get something like this movement that's in the same direction, and that's called wagging. It's a wagging bend. And if they go in, let's say, a twisting motion, like that, that's called a twisting bending, or twisting bend. Actually, we'll put ing in both of these. These are just a few of the possible movements of molecules or groups of atoms, and there's much, much more. So when we look at a spectrum, an IR spectrum, it's going to look pretty complicated, but we're only going to focus on the key absorptions. Okay. So one of the main points here is that the frequency and magnitude of these vibrations affect the absorption of IR light. Affect. And what's interesting here is that it doesn't really absorb any other type of light, not UV, not visible. So these types of vibrations really are um, concerned with the absorption of just IR light. It just happens to be in the right frequency, the right wavelength range. Now, I won't go into the exact correlation of how these movements absorb the light. I'd much rather focus on the interpretation of an IR spectrum. So the next thing we're going to do is look at the features of an IR spectrum. And I printed out two spectra. One is from a textbook, and one is from quality control of a chemical supply company. Okay, they want to make sure that they're selling the pure product. Now, it's actually pretty complicated. We have different labels for the axes, and yeah, we're going to call these either signals or peaks, even though they're going downward. So it's kind of a strange, something that you may not be used to, but the signals are now going down. Okay, so we have a signal at 2900. We'll go over this in just a bit. Okay, what the axes are. But I just want to show you a couple of examples, get a feel for what it looks like in real life. But when we talk about the features of an NMR, sorry, IR, why don't we draw the basic axes? Okay. And I'm going to start with the x-axis. And it has this unusual unit called wave number. Wave number. And the unit is also kind of odd at first. Inverse centimeter. So in the IR range, the wavelength in IR, this might be a little bit tight, but the wavelength is around 2.5 times 10 to the minus 6 meters to 1 times 10 to the minus 5 meters. But to plot on this scale would be a little bit unwieldy. So we're going to convert wavelength into what's called a wave number. I'm not going to show you the actual conversion, but instead of using this as a scale, what's more convenient is graphing the absorption as what's called a wave number. And what it really is, it's waves per centimeter. how many waves pass a certain point per centimeter, or how many waves pass waves per centimeter. Oh no, how many waves are in a centimeter? My bad. Okay. It's actually considered a frequency. Waves per centimeter. How frequent a wave occurs in a centimeter. So sometimes, instead of saying wave number, you just say frequency. Let me put down now the range, because it is kind of unusual. You start on the left at 4,000, and on the right it could go as low as 400. So it goes from high to low. And for instance, we have, I'm just looking at a spectrum right now, and I have, for instance, the signal, something that looks like that. And this occurs at 2900. Okay. In terms of language, and in terms of verbalizing this, you would say that this is a peaker signal at 2900 centimeter, inverse centimeter wave number. So, and we could either call this a wave number, but a lot of times chemists just call it frequency, a frequency at 2900. At 2900 or 2900 inverse centimeter. Okay. So those terms are interchangeable, wave number and frequency. I just want to make sure I'm not forgetting anything. Okay, that is the x-axis. The y-axis is transmittance. And the scale goes from, or the range goes from, sometimes they call the top 100, sometimes they call it 1, and the bottom is 0. So let me go back to the actual spectra. And sometimes it's percent transmittance, 0 to 100, and other times it's just transmittance, 0 to 1. I actually have 0 to 100, so we'll call this percent transmittance. Does this make sense? Because if you have a group of atoms that are absorbing a lot of the light, that means that very little of light is getting through the sample. Very little light is being transmitted. So here you have a sample, okay, and you have a light wave, and then how much of it is coming through. If 100% is transmitted through, then you have no absorption, and that's why we have flat up here. So we're going to say that this area right here, the molecule absorbs very well at 2900 inverse centimeter because it has very low transmittance. So this molecule absorbs very well. And why is it absorbing? It's because it has these vibrations. It has these stretches and bends. That's the physical manifestation of these movements. It's an absorption of light, and it's specifically IR light. Where? IR light at 2900 inverse centimeter. At frequency, 2900 inverse centimeter. The last thing, or one of the last things I do want to make sure that you understand is that, well, okay, great. We have this kind of unusual unit, inverse centimeter, or wave number. What does that mean in terms of energy? And it's very simple. Let me cram it right here. The higher the wave number. Oh, by the way, the wave number symbol, just like wavelength is lambda, wave number has a symbol also. It's kind of weird. It's a frequency with a little bar on top. So that's why also that we could consider these numbers as frequencies. It's waves per centimeter, the frequency of waves per this length of this length. But anyway, the higher the wave number, the greater the energy of the light absorbed. So the appearance of the signal right here, which has a very high wave number, means that the molecule is absorbing fairly high energy of light in the IR range. Now, in a later video, yes, we are going to look at the full spectra or full spectrum. There are certain things that are important, and there are definitely regions that we should definitely ignore because it's way too complicated. Like, we are not going to understand what every single one of these peaks means, but we should understand what the larger or the more we call these stronger signals or longer signals, what they mean. Okay, but that's in a later video. Before we conclude this video, I gotta talk a little bit about a functional group. Okay, functional groups. Because recently the term functional groups has changed a bit. And if IR is used to identify functional groups, we want to make sure that we are talking the same language. So again, IR spectroscopy is great and easy and fast to identify the presence of certain functional groups. Let me draw you a molecule. Oh, by the way, let me just specify. It's great to identify the presence of certain functional groups, but not necessarily where they occur in the molecule. There are limitations to IR spectroscopy, but not necessarily where they are in a molecule. All right. If you're having, I know I'm speaking fast and writing fast. If you're having trouble keeping up, go ahead and pause the video. Make sure you get all of these into your notebook if it's required. Let me draw you a molecule. And we are going to identify some functional groups. So the issue is functional groups are areas of the molecule where a reaction is likely to take place. For instance, we have a functional group here. We have a functional group here. So it's basically all the places where you don't have just a plain hydrocarbon or a saturated hydrocarbon, these alkane parts. Okay, so honestly, I would say that we have 4 functional groups here. But in terms of the terminology, how do we name these? I'll show you how I would name them. Functional groups, and this will be in green. So I would call this a hydroxyl group. And that's how I was taught. I would call this a CC double bond. Some of you may already start to realize, wait a second, that's not how we've learned functional groups. I'll show you the difference. I call this a carboxyl group. And this is a cyano group. I think most people call this an alcohol. To me, that's not really a functional group, that's called a class of molecules. In purple, I think many people and professors call this an alcohol functional group. They call this a alkene. This one is fairly similar. Instead of a carboxyl group, they just call it, most people call it a carboxylic acid. And this cyano group makes this molecule also a nitrile. The way I was taught is the functional group, it identifies the class of molecules. So if a molecule has a hydroxyl group, the molecule is an alcohol. But these days, and this has been happening, I don't know, in the past decade, in textbooks and in my conversations with other professors, when a professor asks for a functional group, that is interchangeable with class of molecules. So let me give you the actual acceptable answer these days. I'll give you another molecule. And here's your OH group. I call it hydroxyl. But let me give you another couple. Maybe this one is something we haven't seen yet in this video. And here we have, let's put a triple bond. Okay. If the exam question is, what are the functional groups? I believe that most professors, including myself now, are really asking the class of molecules, or what portion represents a certain class of molecule. So you would circle this and say this is an alcohol functional group. Do you see the difference? So now, these days, when they ask for a functional group, you actually give the class of molecules. But honestly, it's semantics, they're interchangeable. This is the more acceptable term now for this group, for this FG functional group. So instead of saying this is a carbon-carbon triple bond, this functional group now, you could just call it an alkyne. You're familiar with that. This grouping of atoms is a carbonyl group, but the functional group, the acceptable answer now is a ketone. I just want to go over that because in the next video, when we look at more spectra and we identify what functional groups are represented in this spectrum, what functional groups are represented in this spectrum, we should be using these terms: alcohol, alkyne, ketone, carboxylic acid, nitrile. Historically, those are a class of molecules, but we're going to think of those now as functional groups. I hope that wasn't too confusing. Alright, I will see you in the next video where we will start interpreting and learning how to memorize the different frequencies for each certain functional group.